word on this. Okay. So I'm going to be going over, starting in the middle of this, my last offering for this course on concurrent models of computation. And I haven't looked at these slides in some time, so there's going to be some rough edges here. But let's proceed, and don't hesitate to interrupt me when needed. Okay, I'd like to put this in full screen mode. Right. So metric space semantics. So just first a little bit of background. So the goal here is to talk about the determinacy of discrete event systems and to go over a mathematical model that I think applies pretty directly to lingua franca and that can be used to develop a formal proof of determinacy of lingua franca programs. And there's a long history behind this work. Some of the things I'll be talking about actually date back to the 80s. This notion of using a metric space to develop formal semantics for discrete event systems dates back that far. But it got refined quite a bit in recent years. And the latest refinement that I'm aware of, which I think really sews up the field, was in the work of Eleftherios Matsikoudis, who was a PhD student in my group and then a postdoc in my group. And he basically generalized this metric space approach to handle a lot of corner cases that were not dealt with by the classical technology. In particular, he was able to handle superdense time and integrate that into the formalism very cleanly, and also was able to handle continuous time systems, where you have even mixtures of discrete and continuous behaviors. Okay, so that goes a bit beyond discrete event systems, but I'll focus on discrete event systems for now, because the part that's applicable to lingua franca, the generalization it needs from Eleftherios's work, is the focus on, the ability to support superdense time. Xiaokai, do you know what superdense time is? Because that's probably not in common currency.
My understanding is that it's a two tuple with a timestamp and a microstep. This is
right.
My understanding from the paper, from the lingua franca paper, Semantics.
Right, yeah. So it's a way for time to advance without the metric element of time advancing. I see that Edward has joined. Hello, Edward.
Hello.
We just got started, so you haven't really missed anything yet, except maybe the motivation, which is that we're talking about a mathematical approach for showing determinism in discrete event systems, and that I haven't looked at these slides in a few years, so I might you might have to help me figure out what they say.
All right, looking forward to it.
Yeah, so don't hesitate to interrupt. We are recording this, but I don't really plan to do anything public with it. So, you know, we'll keep it private for whoever, you know, might be able to benefit. Okay, so these slides are in the middle of this class that I used to teach, right? So there's a lot of background, and the students, by the time they see these slides, have seen quite a lot of this kind of notation, but I'll go through the notation with you, and please stop me if anything is puzzling. So a signal here, from the perspective of lingua franca, you can think of a signal as being what flows between two reactors on a connection. Okay, and the signal is a partial function in this formalism from a model of time, t. So t is a set of time values. In the classical way of approaching time, t is just the non-negative reals. Okay. In lingua franca, it's richer than that because it's super dense time. It's the non-negative reals with a microstep index. And both of these sets T are totally ordered sets. And in the case of super dense time, it's what we call a lexicographic order or a dictionary order. So two time values are ordered first by the real number and second by the microstep index. If you have two time values where the real number is equal, then the microstep index will define the order between them. Okay. Now, the signal being a partial function is a way of modeling the absence of a value. So the way that we model this is that, well, actually, there's two uses of this in the formalism, and I think the use in these slides is actually that the signal will be defined up to a point in time for all times up to that point, and then undefined beyond that. And that reflects an incremental computation of the signal. Okay. There's an alternative use where you define the function so that it's undefined whenever the signal is absent, when there's no event at that particular time. But I think it'll become clear which of those two we're using, hopefully, in the next few slides. But
so by undefined, do you mean unknown or absent?
Well, so in the formulation where you use undefined for absent, then it means undefined. This function being undefined at a t means that the signal is absent. So if the signal is unknown at that time, then you don't know whether the function is defined or not.
Right.
Right. So that would be the formalism, okay? But I'm not sure that's the formalism that's used in these slides. We'll find out in a couple of slides. I don't really remember which of the two is used, okay? All right, so the tag set, actually it looks like this is definitely using the version where undefined means absent. Okay, so the tag set of a signal is a subset of T, and it's the set where it's not absent. Okay, so those are the time values where there's an event. Given that definition of a signal, then the signal can be represented by its graph, which is a set of time value pairs. Okay, so the graph of the signal is the time value pairs. The signal itself is a function from time values to, or a partial function from time values to the set of values. Okay, then in this notation, if you put parentheses around this, this is simply the set of all signals. And so in lingua franca, signals are generally discrete, okay? Not always, but discrete has a very technical definition. All right, so a signal is discrete if there is an order embedding between the tag set of the signal and the natural numbers, okay? And an order embedding is a technical term. So what it means intuitively is that a signal is discrete if, when you list out the times at which the signal is present, that you can enumerate those. There's a first one, there's a second one, there's a third one, etc. And that enumeration covers all the signals. Okay, and this is probably a good chance to switch to the iPad. I'll try and see if this works. All right. It counts down to broadcast. Okay. Cannot start while another. Okay. How do I stop this then? Stop sharing. Okay. I am screen sharing. All right. How do I get to notability? All right. So if you have your set of times on the horizontal axis and you have events occurring at particular times, okay, these tags, so you could have the first tag, the second tag, the third tag, and so forth. If these can be enumerated in numerical order, it's a discrete set. And an example of a signal that is not discrete, somewhat counterintuitively, is one where you have an infinite number of events before some finite time, and then more events after that. Okay? And the reason this is not discrete is because there is no mapping there is no order preserving mapping from the time tags of the signals to the natural numbers. All right, because these guys are past infinity, right? There's an infinite number of events here. So this is tag sub infinity 1, this is tag sub infinity 2, and so forth, right? So you can model this using transfinite numbers and so on, but the simplest case, which I think is the case we want to deal with lingua franca, is that you simply disallow programs that have this kind of behavior, and then we're always dealing with discrete signals. Okay, so these kinds of signals are called xenosignals, and there's lots of papers about exploring the corner case of xenosignals in discrete event systems. And personally, I find them of theoretical interest, but not really of practical interest. Okay, so let's see, I can stop sharing. Back to the slides. Whoops. Okay, so we're just going to focus on discrete signals, which means that the tag sets can be enumerated. Okay, so an actor, which we will want to redo this for reactors, and I think the changes would be really rather small, but in this formalism, an actor is formally defined by a function capital F that maps an m tuple of input signals to an n tuple of output signals. Okay, and it's really important to understand that this is not a function mapping events to events. This is a function mapping entire signals to entire signals. Okay, now when you have such a function, this actor is deterministic. Okay, and in fact, this is really what we mean by having a deterministic actor, is that if you know the entire input signals, you know the entire output signals. All right. If you can't define a function from inputs to outputs, it's a non-deterministic actor, right? There may be, for a given input, there might be multiple possible outputs. Now, one subtle corner case is, what about functions that have no inputs, right? So you can have a reactor with no input ports, just it only has output ports. How do you model that? Well, in this formalism, if m is 0, okay, then the set of functions raised to the 0th power is by definition a singleton set. It's a set with only one element, all right? So that means that the function f is a function whose domain has only a single element and whose codomain is an n tuple of signals, if it produces exactly one n tuple of signals, given that one input, there's only one possible input because it's a singleton set, then it's deterministic, right? So the definition works fine for a deterministic actor, even if there are no inputs. And similarly, with no outputs, the codomain becomes a singleton set. So the function always yields the same value for all inputs. And consequently, every reactor with no outputs is deterministic. Okay. By the way, the intuition here, the reason you can think of naturally raising a set to the 0th power being a singleton set, it's analogous to algebra, right? Where you raise any number to the 0th power and the result is 1. Okay, by definition of exponentiation.
In the case of reactors, however, it might make sense to actually model actions or timers rather than model them as, you know, not being present, there not being any ports. We might actually want to model them as ports.
Could be, but then you're going to have the challenge of having to integrate a multiplicity of timelines, right? So consider this simple case where you have a reactor that has a single physical action and a single output port. Okay, one way to model this is to say, well, I'm going to define the function f, capital F, to be just one observed behavior of that reactor. Okay, so for each behavior, it's a completely different situation. I'm getting an interrupt here. Is that?
It turns out this is a bad time.
Well, yeah, maybe why don't you show Inderjit what the deal is? And hi, I'm sorry, I'm on a conference call.
Okay. I can take a look.
Yeah,
so
and
come around and meet you back there.
but there's two possibilities. One, can you explain the issue about just patching versus removing the whole deck?
I guess so.
Okay, those are two alternative outcomes of this thing. I told this guy I was available until 10 o'clock, and I think he interpreted that to mean I was available after 10 o'clock. Anyway, okay, right. So if you model that reactor and its actions, where the function f represents a single behavior, right? This is kind of what we mean when we talk about a lingua franca program is deterministic under the assumption that you consider the timestamps assigned by physical actions to be part of your input, okay, or part of your function definition. In this case, they become part of the function definition. So for a particular capital F representing the events produced by that physical action, the rest of the program will be deterministic.
Yeah, so this is kind of the difference between an implementation and its environment. But I guess that the modeling works if there's no feedback. So if you're talking about physical actions that just get a timestamp based on what happens in the physical world, I think that's a sound abstraction. But we also have logical action, which are scheduled from the functionality of the reactor and then drive later responses. So maybe in that case, it wouldn't be fair to say that that F would be independent of Fn.
I think that you could you could extend this to include the feedback through the physical world, but you would have to model the physical world as well using similar functions. Okay.
Right. So I agree with that, and I think that for the physical actions, it makes sense to model it exactly the way you described. But if you have the logical actions, which are scheduled, synchronously, then it seems to me that it would make sense to also be able to, I guess, predict the behavior of the signal.
Hold on 1 second. Okay, can we take a 5-minute break? Sorry about that.
Yeah, no worries.
Let me pause the recording. If I can figure out how to do that. Okay, resume recording.
So Edward, what I was trying to get at earlier was that logical actions, that we can model them as little feedback loops with a delay in them.
Oh,
In
sure,
that case, you
but
can actually model the port, the action as a port, right?
yeah, you could, but you don't really need to. And in fact, it doesn't really buy you anything because you still have to model the time delay. And so you might as well just model it inside the reactor that has that logical action. Right? It doesn't really buy you anything to separate it out because you still need then you need a primitive for a time delay.
Gotcha.
Okay. All right. So now this is a reminder that absolutely any network of reactors can be converted into this. Okay. So everything is a feedback problem. And this is a little bit counterintuitive, right? But if I show you on my iPad, it's a little awkward going back and forth constantly. It'd be nicer if there was a way to share simultaneously. Let's erase all this.
I think there might be. I think that you can set you can allow multiple people to present simultaneously so that you don't have to switch.
Yeah, I think I tried that once and I couldn't get it to have both presentations show up. Okay, so imagine, this would look like a simple counterexample, right? That's not a feedback loop, but actually it is, right? If this is reactor A, this is reactor B, all I have to do is redraw them like this, and it's a feedback loop, right? And so the capital F that we're interested in is this one. Okay, so any network of reactors, no matter what the interconnection topology, can be reduced to this, where this is a vector of signals. Okay, and once you've reduced it to this, when you have this capital F function, that means that you're looking for a vector of signals such that f of s equals s. Okay. And in fact, the meaning of the program, of the lingua franca program, is the s that satisfies this equation. And so the question of whether a program is deterministic is simply a question of whether S exists, there is an S that satisfies this, and whether there's more than one S that satisfies this. If there is exactly one S that satisfies this equation, the program is deterministic. Okay. All right, so So the question then is, you know, what we want to do is use algebraic properties of the function f to show that the function f always has exactly one fixed point. And in fact, we can go a step further and we can give a constructive procedure for finding that fixed point. And that constructive procedure is actually something, it gives you an operational semantics for the program. And you'll see that the constructive procedure that we get using the metric space formulation is a very good description of what we actually do when we execute these programs. Okay. All right. So what is a metric space? So a metric space is a set and a distance function. And in the classical metric space definition, the distance function takes two arguments from the set and returns a non-negative real number, which is a measure of the distance between those two elements of the set. Okay. And the metric, the function d is called a metric, and it has to satisfy the property that if the two elements, if you give it the same element, you get 0. So this is called the identity of indiscernibles. So if two elements of the set have a 0 distance, they're the same element. Okay. The other is symmetry, which is that the distance from x to y is the same as the distance from y to x. And then finally, the triangle inequality, which is that the distance from x to z is less than or equal to the distance from x to y plus the distance from y to z for any y. Okay? So any function that satisfies those three properties is a metric. An ultrametric is a stronger thing. It's also a metric, but instead of the triangle inequality, the distance between x and z is less than or equal to the maximum of the distance between x and y and the distance between y and z for any y. Okay, that's called an ultrametric. And d will be called an ultrametric distance function. Right, and it's going to turn out that everything we're going to use is going to be an ultrametric, actually. And that's a nice property because maximization is a more primitive operation than addition. All you need is an ordered set. You don't need an algebra to do maximization. So in fact, we'll use this right away with the Cantor metric. So the Cantor metric is really cute, okay? So if you consider your set X to be the set of all signals, now we're not using superdense time. So the signal is mapping real time, real numbered time to values, okay? Consider two signals in that set. And suppose that those two signals are identical up to, but possibly not including some time tau. Okay, so you got two signals that go along in time and are perfectly the same. And then at some time tau, they differ. So the Cantor metric is a function that just is 1/2 to the tau, where tau is the smallest time at which the two signals differ. Okay, it's also called the Baire distance in some of the literature. So this is very cute, and it's also very intuitive, right? What happens if S1 and S2 are actually identical for all time?
Then the distance would be 0.
Distance is 0, right? Because tau goes to infinity, and 1/2 to the infinity is 0. So two signals that are identical for all time have a distance between them of 0. So that works out. You got identity of indiscernibles. If you have two signals that differ right at the beginning at time 0, then you have 1/2 to the 0. Okay, 2 to the 0 is 1. So the distance is never greater than 1 in this case with this formulation. That's as far apart as two signals can be as 1. Okay, so let's look at a couple more examples. So suppose the graph of S1 is this, which means at time 1, it has value 0. And this guy at time 1 has value 0, and at time 2 has value 0. Then what's the distance between these? So you take 1 over 2 to the tau, where tau is the earliest time at which they differ. The earliest time at which they differ is 2. So 1 over 2 to the 2, distance is 1/4. Okay. Suppose you try to make time the entire real line. Okay, not just the non-negative reals, right? So with non-negative reals, you never get a distance bigger than 1. All right, so let's make time bigger. So there's no time origin. So now suppose that you have, for all integers, a signal that has value 0, and another signal that for all integers has value 1. So now the earliest time at which these differ is -infinity. Okay, you could think of it that way, which means your Cantor metric would be 1 over 2 to the -infinity, which is 2 to the infinity, which is infinity. So these two signals are infinitely far apart. And that, in fact, disqualifies it from being a metric, okay? Because by definition, a metric is a mapping into non-negative reals, and infinity is by definition not allowed. So if you try to turn this into a metric space, you'll find that it's not a metric space. You're going to need some generalization of a metric space to handle this. Okay. All right. So you can get into some weird corner cases with Zeno signals and continuous time signals about what is the earliest, what do you mean exactly by the earliest time at which they differ? But I don't think that's very important for our purposes. So in lingua franca, it's always going to be clear what the earliest time at which two signals differ. And so as long as you disallow Zeno signals. By the way, in some ways, we disallow Zeno signals in lingua franca by construction, because time is an integer, not a real number, right? So if time is incrementing in nanoseconds, then we can't get Zeno signals that way. Okay, so the mathematical corner cases basically don't arise.
But logical actions can be scheduled at the current logical time, in which case they incur a microstep delay, and that gives you Zeno B.
Right, and we can get Zeno signals that way by incrementing the microstep without bound. That's right. Good point. Yeah, so that's the way you would get Zeno signals in lingua franca. Yeah. All right. What is this? Okay, this is just saying that if your timeline is the non-negative reals, your distance is always between 0 and 1. Okay. Oops. So the Cantor metric is actually an ultrametric. It's not just a metric. It satisfies this maximum instead of the triangle inequality. And I think it's, you can take my word for it or look at the proof later if you're interested, but it doesn't really matter for our purposes. Okay. All right. There's a relationship between the Cantor metric and causality. Okay, and this is really one of the most interesting properties of this. So if you have an actor that maps, say, we'll start with just one signal into one input signal into one output signal. Okay, then by definition, this actor is causal if for all possible pairs of inputs, that the distance between the outputs is less than or equal to the distance between the inputs. Okay. Okay, so what does that really mean? That means that if you can have two possible inputs for the actor, and they're identical up to some time tau, then the outputs will be identical up to that time tau. Okay? The time at which the outputs differ cannot be earlier than the time at which the inputs differ. So that's a mathematical capture of the notion of causality, which says that the outputs can't anticipate the inputs. Okay, you can't have outputs that differ before the inputs differ. So that's causal. Causal is less than or equals. Strictly causal is less than. That means that the outputs always differ later than the inputs differ. And delta causal is where there exists a real number less than one that you use, so the distance is, at least delta times the distance between the inputs. And what this translates into is that there's a lower bound on the delay. So if the inputs differ at time tau, the outputs will not differ until sometime tau plus delta, and there's a lower bound on delta. Okay? So these are three distinct representations of causality, and delta causality is the simplest one, and I'll show you how we use that in a minute. Okay. So these are Ptolemy actors, right? If you just have an...
Sorry to interrupt. Can you go back one slide?
Sure.
So the causality here we're discussing, I see that we're using a special case of two signals in the system. Does that apply to more signals? For example, there's an S3.
This should be read as for all S1 and S2.
Okay.
Okay. So for any two possible input signals, if they differ at a certain point, the output will differ at that point or later. Okay.
Got it.
So that's the relationship between the notion of causality and the notion of this metric. Okay, that's part of this is the real beauty of the Cantor metric, is that it gives you this very clean definition of causality, and it's an algebraic property that we can use to prove what I'll show you is that in any feedback system, if capital F is delta causal, there's a classic theorem that says there is exactly one fixed point, and there's a procedure for finding that fixed point that actually matches what we do when we execute these programs. Okay, but that theorem only works for delta causal systems, so you have to generalize the theory to handle strictly causal systems and causal systems, which we're interested in.
Got it, thanks.
Okay, so if you have a reactor that just takes an event with a number in and produces an event that scales that number by some number, that's causal. Okay, a register which is clocked to produce an output. This is modeling, for example, a register in hardware. That's strictly causal, and a time delay is delta causal. Okay. So if you have logical actions, for example, that are being used to create time delays, you would end up with delta causal actors. So this is a counterexample that shows that there's corner cases where if you don't have this nice property of discreteness everywhere, if Zeno signals are possible or continuous time signals are possible, things can break down. But I think we can leave the corner cases aside for the moment. This is about the corner case. Okay, so let's get to the fixed point theorem. So there's a classical notion in metric spaces of a contracting function. Okay, so a contracting function is a function that maps a set into itself. Okay, And the set is a metric space. And a function is said to be contracting if it satisfies this now familiar looking property, right? So in the case of the Cantor metric, it's causal. But this is more general because this applies to any metric space. So the intuition here for the term contracting is that if you have, think of suppose your X is three-dimensional space, and you got two particles in three-dimensional space, and you apply your function to them, they get closer together. Okay, that's where the term contracting comes from. They have a certain distance apart. Before you apply the function, they get closer together. All right. Contracting really says you apply the function and they don't get further apart. Strictly contracting says they actually do get closer together. And delta contracting says they get closer together by some non-zero amount. Okay. Now this relates very nicely to fixed points, right? Because what happens now, if you keep applying a contracting function over and over again to this pair of points that are getting closer and closer together, they eventually converge to a single point. Okay. That's the intuition behind the fixed point theorem that we're going to use, that you can use to prove determinism. Okay, so this can be generalized to multiple inputs and multiple outputs. We just say that we generalize the Cantor metric so that tau is the earliest time at which any of the inputs in the tuple of inputs differs. Okay, and similarly for the outputs. So that's a fairly straightforward generalization. It also works when you have no inputs and no outputs. Okay, when the number of inputs goes to 0 or the number of outputs goes to 0. In that case, it degenerates in kind of curious ways. So we can look at, for example, when there's no inputs, then the set of all possible input signals is a singleton set. Every pair of inputs is identical. So the distance between any two possible inputs is always 0. Okay. And so a causal function is just going to be, well, all functions are going to be causal, because if it's a function, you know, there's only one possible input, there's only one possible output. The distance between all of pairs of possible outputs is also 0. So a function with no inputs is always, in fact, delta causal, strictly causal, and causal, all three. Okay, so that's what I just said. So this function with no inputs is delta causal and delta contracting with delta equals 0. And similarly, a function with no outputs is also delta contracting with delta equals 0. Okay, so now we can connect to the fixed point theorem. So the first fixed point theorem is that if you have a metric space and a strictly contracting function, then the function f has at most one fixed point. Okay, so this says that if you get a behavior, you won't get more than one behavior. But it leaves open the possibility that there is no behavior, that there is no function, there is no x that satisfies this function, that is a fixed point, right? That's for strictly contracting. For delta contracting, I won't go through the proof of this, right? Let me skip ahead briefly and then I'm going to come back. Okay, for delta contracting, then the function f has a unique fixed point. So it eliminates the possibility of there being no behavior, and it gives a procedure for finding that fixed point. And I'll show you in a minute how this procedure is in fact what we do when we execute a lingua franca program. Okay, but let me go back a little bit and go through a couple of examples because I think the examples are important to understand this. So we go back to this first fixed point theorem, which is that if you have a strictly contracting function, then f has at most one fixed point. Okay, so what if you have, if you're looking at R kinds of signals, right? So X is the set of signals, and your function is a unit delay. Okay, so capital F, given an event at an input event at some time t, outputs an event, the same event at time t plus 1. Okay, now put this unit delay in a feedback loop. What's the fixed point? Right, this function is going to be delta contracting because the unit delay has a lower bound on the delay between the input and the output. So think about it intuitively. If you have a reactor that reacts to an input using a logical action to schedule an output 1 time unit later, 1 millisecond later, put that reactor in a feedback loop, what's it going to do? Fire up your lingua franca compiler and try it.
I'm having a bit of trouble connecting the idea of fixed point to a lingua franca setting.
So
not
it would
really-
just shift the entire signal?
But what entire signal, right? We want to find what that signal is. What is going to be the behavior of that lingua franca program?
So this is a, yeah, maybe you can draw it.
Yeah, let me draw it. I don't know how to use this program very well, but let me see if I can just, oh, okay. Now I can just add another page. All right, so I have a reactor and it's got a reaction to an input that schedules a logical action that I didn't make this big enough. Oops. My watch is telling me my timer's done. I didn't set a timer. Okay, so there's our lingua franca program. And all it does is given an event at the input with some timestamp t, produces an event with timestamp t plus 1. And we connect its output to its input. There's no causality loop here because of the logical action. So what will this program do? Come on, guys.
This
We'll
would,
keep going.
You guys need to write more lingua franca programs.
this would depend on what the first reaction does, right? I mean,
Let's suppose that, okay, yeah, you're right. So let's suppose the reaction, all it does is schedule this logical action with the value of the input.
okay.
And then when the logical action triggers, it takes the value of the action and produces it on the output.
So the value will be absent, so it will schedule it with absent, and yeah, it will just produce a sequence of absent.
Well, we don't get sequences of absence in lingua franca.
So then it's the singular, or what is it, singleton? There's no behavior.
There's a behavior. If you write and compile it, should we do it? Let's write this program. It's actually worth doing this exercise, I think, because it'll give confidence in the theory. I guess I have to start sharing again. Seems to be rebuilding my project here for some reason.
And so the second reaction just outputs the whatever it receives, or what does it?
Yeah.
What does it output?
So let's write it. Call it delay LF. This is what we didn't see because there was no overloading. Schedule A at, let's just say 100 milliseconds delay with value X. And then reaction to A will produce Y. Set Y to A, I think, is the syntax. Is that right? Oops, get a compiler. Oh, why does it say, there's no cycle. Oh, yes, there is. Bingo. Okay, now it compiles. So now I can run it.
Actually, Edward, could you send me the model that was triggering the error message? Because that error message, have you recently pulled in changes or not?
Not today.
Have you done so yesterday, maybe?
Yeah, I pulled
Because because that error message came from the code generator, and it should have come from the validator. So I'm worried that maybe there's something wrong there.
Okay, well, let's pursue that separately. I am saving this file. So. Okay, so let's see, I think I did. It runs.
Yeah, but we haven't printed any values, right? So
okay, shall we print a value? So let's,
Don't we need a startup?
okay. Run it again. Same behavior. All right.
But
It's the right behavior.
okay, so when I said no behavior,
In
that's what
response
I
to an
said.
input event, this will schedule a logical action. In
Mhm.
response to that logical action, it will produce an output.
Right?
No input event ever occurs, so no logical action ever gets scheduled, so no output ever gets produced.
Right.
Okay? So let's go back to the formalism. So this is a function that maps this set into itself. It's a unit delay, and you put it in a feedback loop. And the question is, what function will satisfy that fixed point? Okay, so let's go back to the iPad. This is really awkward going back and forth. I wish there were a better way to do this. So this guy, whenever there's an input, produces an output with one time unit later. We're looking for a signal S where f of s equals s. So every event in S will appear here one time step later. What are the possible values for S? There's only one, the empty signal. Any other possibility fails, right? If I try to make S a signal that has an event at time tau, then f of s will have an event at time tau plus 1. These two are not equal, so they can't be a fixed point. Okay. So I could say, well, S is has an event every one time unit. Okay, but that still doesn't work because of the first event being missing in f of s.
Mhm.
So the only possible fixed point here is the empty signal. Okay, and the Banach fixed point theorem tells us that. And it'll actually give us a procedure for finding that. And it's actually a fairly remarkable procedure. I'll show you what the procedure is, okay? So we have a function f, and we're looking for an S such that f of s equals s. Okay? And f is delta contracting. The Banach fixed point theorem says start with any signal. Who cares? Doesn't matter. Okay, so let's start with, why don't we start with the signal that I showed was problematic, tau. It has an event at time, let's make it concrete, at time 1. Okay, so this is time 1. Then the Banach fixed point theorem says, apply your function f, and you get a new function, okay? Something at time 2. Apply it again, and you get a new signal, now at time 3. do this forever, okay? And the limit of the sequence is your fixed point. So what's the limit of the sequence? Well, the limit of the sequence in this case pushes this event out to infinity. The limit of the sequence is the empty signal. The event never occurs. There's never an event.
So how do you go from infinity to empty signal?
Does that make sense?
Well, except from the jump you make from infinity to the,
I see some
to the empty
skepticism.
signal. Can you hear me, or?
You guys aren't quite buying it.
Oh, I don't think Edward.
It's a little hard to internalize.
So Edward, can you actually?
So one
hear
of the
me, or-
interesting things here is that
I don't think so.
if you allow time to last forever, okay, then there actually is an alternative fixed point. If there's no time origin, right? You could, if you have a unit time delay, you could have a signal that has an event every one time unit. And that will also be a fixed point. In fact, you could have it have any value at that one time unit. So there's an infinite number of fixed points. But that doesn't contradict the theory, because this set of signals is not a metric space. Okay. There's actually a very beautiful generalization of this that is due to Xiaojun Liu, one of my PhD students. He made the observation that if you actually allow time to go infinitely far back into the past, then you can think of it as your universe splits into an infinite number of universes where all signals in distinct universes are infinitely far apart from each other. So it actually gives you, in some ways, a way of mathematically modeling the many worlds interpretation of quantum mechanics, which is a really bizarre way of thinking about it. But you know, you can think of it as all of those possible fixed points of the unit delay exist in universes that are infinitely far apart from one another. Every one of them is a fixed point, but they're infinitely far apart, so they can't have any influence on each other. So they exist in different universes. That's an absolutely wild interpretation of this, but you know, it basically says that if you have no time origin, the universe splits into an infinite number of universes. Okay, so let's see, what is this? Oh, this is talking about convergence. Okay, and convergence requires a notion of a metric, right? Because an element in the set is the limit of a sequence if for all epsilon greater than 0, there exists an n such that for all k greater than n, the distance is less than epsilon. So when you think of this unit delay pushing the event out to infinity, okay, at any point, you know, you're iterating this function over and over again. The event never disappears, okay? But the distance between the signal and the empty signal gets smaller and smaller, right? As you keep pushing the event out to infinity, the first time at which that signal differs from the empty signal gets later and later. So tau in the 1/2 to the tau gets bigger and bigger. So each of those signals in the sequence, as you keep applying that function, is getting closer and closer in this Cantor metric to the empty signal. And you can, in fact, apply exactly this notion of a limit. Set any epsilon, and
explains it.
no matter how small your epsilon is, there will always be some point in your sequence where the event is so far in the future, it doesn't matter anymore. Okay? That's essentially what this is saying. So in that sense, this sequence of applications of the function f does in fact converge to the empty signal. Okay. Oops. Okay, so if you look at, sequences that are converging, so what I just pointed out was that if you have an event, a set of signals where the event occurs first at time 1, then at time 2, in the second sequence, in the second signal, and so on, that this sequence converges to the empty signal. What about a sequence that has events? The first signal just has one event at time 1. The second one has an event at time 1 and an event at time 2. The third one has an event at time 1, then 2, then 3, and so forth. Well, in the same sense, this will converge to a signal that has an event at all integer times. What about a Zeno signal? So a Zeno sequence, rather. So this is, again, let me sketch it.
Hi, Edward, can you hear us? Can you hear me?
So
Yeah, I can hear you.
the first signal in our sequence.
Well, I can hear you, but Edward can't.
Yeah, Edward can't.
Has an event. What did it say? One time is
Somebody text him.
1 minus
I mean, I can hear all of you.
1 over 2 to the n. So if n is 0, then there's an event at time 0.
Edward.
Okay. For signal 1, whoops, I can't hear any of you. That's true. You're all muted.
The lecture must go on.
Also, when we're not muted.
Hello,
See,
can
I'm
you-
talking, but you can't hear me.
You're still muted.
Can you hear me? Hello?
Hello, 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 world.
Hello,
Okay.
world.
Oh, huh. There we go. Sorry about that. I guess I must have muted my audio on my end. I don't know why. Sorry about that. So what were you trying to say?
I just had a comment. I just find it pretty fascinating that, as the event keep pushing to infinity, it's actually converging to the empty signal, due to the Cantor metric.
Right.
This is interesting to think about.
It has so many implications, and there's lots of reasons for this to be an appealing mathematical model, right? But let's look at this Zeno case, right? So suppose you have the first signal just has an event at time 0. The second signal has an event at time 0 plus another event at time 1/2. Okay. The third signal has those same two events, but an additional event at time 3/4. Okay. And so forth. The next one, S3, has an event at time 0, an event at time here, an event at 3/4, and an event at 7/8. And you keep going. What does this signal converge to? Actually, the signal doesn't converge. Okay, this sequence doesn't converge. Think of it, you might think intuitively that it converges to the signal that has an infinite number of events up to but not including time 1, right? But every signal in this sequence, what's the distance between that signal in the sequence and that ultimate signal? What's the earliest time at which those two signals differ? That earliest time is always going to be less than 1. So by the Cantor metric, the distance between every element of this sequence and what it intuitively converges to is the distance is greater than or equal to 1/2. Every element of the sequence is at least distance 1/2 from the signal that it seems to be converging to, which is not convergence. Okay? So that, so this sequence of signals does not converge, in fact. Notice that if you try to construct this using a lingua franca model with a little feedback system, what are you going to have to do? You're going to have to keep decreasing the time delay in your logical action and making it always smaller than the previous time delay, which means that function is not going to be delta causal. So the theory says, I can't give you a behavior. Okay, at least based on the Banach fixed point theorem. Now, I'll show you how you can generalize this so that it actually does, the theory can be extended to actually describe what the lingua franca program would do if you allowed this behavior. But, you know, I mean, at some point in the lingua franca program, you're going to get down to incrementing time by less than a nanosecond. Your only choice is going to be to fall over to microsteps to increment time. And eventually you'll run out of microsteps because we only use a 32-bit number to represent microsteps. So the program will break down eventually. Okay, so in these latter two cases, right, you can think of the sequence of signals in this sequence as being an incremental buildup of a behavior. Okay, so here's the Banach fixed point theorem. It says that if you have a complete metric space, and completeness is a technicality that we need, but it turns out all of our metric spaces are complete. So, and the function is delta contracting, then it has a unique fixed point, and the following sequence converges to that fixed point, regardless of your starting point. Now, in an actual execution of lingua franca, what we do is we always start with the empty signal. Okay, and then start iterating these functions, and that'll actually give us a constructive procedure for finding the behavior of lingua franca. But the Banach fixed point theorem says you don't even have to start with the empty signal, you can start with anything. Right, and it'll still converge. So this, okay, so we already looked at why this Zeno doesn't converge, right? And so by the Banach fixed point theorem, either the metric space is not complete or F is not delta contracting. And there's some slides here that go into technically what completeness is about. And you can go through and show that our metric space is complete. So there's no problem with completeness, which means that it has to be, yeah, so here's the theorem, that the set of discrete signals, okay, you have to restrict this to discrete signals, is a complete metric space. And anyway, you can go through my slides for proof of that. So non-completeness is not the problem here, so it must be that f is not delta contracting. And in fact, this is a Ptolemy model, which you could re-implement this in lingua franca, that just uses a variable time delay, delays an event, so injects a single event into a loop, calculates a delay that keeps decreasing. Okay, so each time it uses a smaller delay. This is a plot of the signal. That's how you can construct that, and that does not, in fact, converge under the Banach fixed point theorem. You could also do something like this, where you use a random delay, okay, in a feedback loop. And this random delay here is strictly causal, but not delta causal, okay? And you can go through and show that this will be non-zeno with probability 1, but the Banach fixed point theorem provides no assurance. It's not a probabilistic theorem, it's an algebraic theorem. So probability 1 is not good enough. Okay. Okay, that's that about the Banach fixed point theorem. And so now what I'd like to do is give you one more concept, right? And then I think it'll be enough for one day. But I'd like to I'd like you to see to get a little bit of a flavor for what the extensions of this look like that can handle Zeno conditions, that can handle superdense time, and that can handle continuous time signals. Okay, and they're really cute. I love the math that comes out of this, and so so the Cantor metric is just reviewed here, and one of the key properties of a metric space is that the metric is always a real number. It's a non-negative real number. That's by definition of a metric space. A distance is always a non-negative real number. Well, it turns out there's generalizations of that idea. You can generalize the idea of a metric so that the distance function doesn't have to give you a number. It can give you something different from a number, like a member of a totally ordered set. Okay. So here is a notion of a generalized ultrametric space. So a generalized ultrametric space is a set X and a distance function, where the distance function takes two elements of X and gives you an element of a new set. And the only requirement on this set, you remember with the Cantor metric, this is the non-negative reals. But with this generalization, all we need is for this to be a partially ordered set with a least element. It's called a pointed poset. Right? If you have any set that has a least element and has a partial order, you don't even need a total order. Okay? Then you can get a generalized ultrametric if it satisfies the following properties, which is that the distance is equal to the bottom element of your set if and only if X equals Y. So that's the same as the distance being 0. This is the identity of indiscernibles. You need symmetry. And then you need this generalized ultrametric inequality, which is that if the distance between X and Y is less than or equal to some gamma in the partial order, this is a partial order relation, and the distance between Y and Z is also less than or equal to gamma, then it has to be true that the distance between X and Z is less than or equal to gamma. Okay? So if you satisfy these three properties, you have a generalized ultrametric space. So here's where, whoops, I just went to the references. mean to follow that link. This is where the contributions from my PhD students start to come in. And okay, we were here.
The contribution from Haiyang, if I remember correctly.
No, this was after Haiyang. The key contributors to this were Adam Cataldo, Xiaojun Liu, and Eleftherios Matsikoudis. Those three guys. Okay, so we have this notion of a generalized ultrametric space, and we can define contracting functions and strictly contracting functions on the generalized ultrametric space, but there's not even a notion of delta contracting. Because if you remember, delta contracting requires multiplying the distance by some real number delta. All we've got, our distance is giving us a member of a poset with no algebraic properties required at all. We certainly don't have multiplication. We don't have multiplication by a scalar. There isn't even a delta contracting notion, right? So it turns out we're only going to be able to work with strictly contracting. This is a little tongue-in-cheek, but Bajaj was one of the students in my class, and we kept getting frustrated by the fact that this theorem had no name. So I named it the Bajaj theorem because he was, I asked someone in the class, can someone prove this theorem, right? When this like the second or third time I came back to it, and Bajaj raised his hand and proved it, just instantly. So I named it after him.
I'm assuming that's Nikunj.
Yes, exactly. So anyway, so this was this classic theorem that if you have XD in a metric space and you have a strictly contracting function, then f has at most one fixed point. There's a corresponding theorem for an ultrametric space, which requires a few more technicalities. This notion of spherically complete, which is again, you can take my word for it. Our spaces are going to be spherically complete, but you need this technicality, okay? And you have a strictly contracting function, then f has a unique fixed point. So it's actually a stronger theorem for strictly contracting. Whereas the previous, with the metric space, it just says it has at most one fixed point. Here it says it has a fixed point and it's unique. It turns out, interestingly enough, there may be no constructive procedure for finding that fixed point, but there is a fixed point and it's unique. Okay. So the first contribution from my group was actually giving a constructive version of this theorem, and that was Adam Cataldo's work. And for our context, we got a constructive theorem. But then the most interesting part about this is how these guys actually constructed the metric space. So here's their definition of the generalized ultrametric space on time signals. Okay, so we consider the set gamma to be a set of lower sets of times. Okay, so each element of this set is the set of all times up to some time, from the starting time to the ending time. All right, so as soon as you've got that's called a lower set because it includes all the earlier times. Right? So the set of all lower sets of times with reverse set inclusion as the order relation, that's going to be our metric. Okay, the metric function will yield an element of this set. So the generalized ultrametric distance function, given two signals, gives us the set of all times on which these signals are identical. Okay, so now instead of getting a number 1/2 to the tau, your distance metric gives you a set of times over which the signals are identical. So if the signals are always identical, then you get the entire timeline. which is the largest possible value under this reverse set inclusion order relation. No, the smallest possible value. So if two signals are identical, your distance metric gives you the entire timeline. Your order relation is reverse set inclusion, so the entire timeline is the smallest element of this set. It's the least element. So the distance is least when the signals are all the same, or always the same. And as the time at which the signals differ gets earlier and earlier, the distance gets larger in this reverse set inclusion sense, because the set of times gets smaller, okay? And smaller sets here are going to be larger in reverse set inclusion. Okay, so this turns out to be a generalized ultrametric distance function. And it is actually stronger than that. It's a generalized ultrametric semilattice, which means that a whole new family of fixed point theorems kicks in. Okay, so a semilattice is a kind of partially ordered set where every two elements of the lattice has a least upper bound. Okay, and I won't go into the details here, but I'll just sort of tell you the punchline, which is that this theory handles any totally ordered tag set. You could have the non-negative reals, you can have the integers, even with no time origin. You can have the natural numbers, you can have the reals with no time origin, you can have superdense time, okay, etc. In fact, any totally ordered tag set, this builds a fixed point theory around it. These two statements are due to Eleftherios Matsikoudis, and they turn out to be really kind of beautiful statements about that you can use over and over again to prove a lot of properties of the signals. It says that if you have an S1 where the distance between S1 and S2 is less than the distance between S1 and S3, then it turns out the least upper bound of two signals is their common prefix. Okay, in this theory, it ends up being that you can order the signals, and if you form this is like a set intersection, but it's called a least upper bound. The least upper bound of two signals is the common prefix. So this says that the common prefix of S1 and S3 is a prefix of the common prefix of S1 and S2. Okay. It also says that the distance between the common prefix of S1 and S2 and the common prefix of S1 and S3 is less than or equal to the distance between S2 and S3. These have very nice intuitive interpretations, and you can just, you sort of have to sit down and think through a few examples to understand what they mean, but they're actually very intuitive lemmas. And Eleftherios proved these lemmas and then proved a whole bunch of theorems using these lemmas. Let's see if there's more that I can say about this. Oh yeah, causality and contracting functions. Recall that a contracting function had this property, and now in this generalized ultrametric, it's a reverse subset relation. Okay, and this is consistent with the notion of causality, because a function is said to be causal if two input sequences with a common prefix that extends to time tau, if those yield two output sequences with a common prefix, the common prefix of the output will extend at least to time tau. Okay, so it's kind of the same result that we got with the Cantor metric, but it generalizes to all these other possible timelines, which the Cantor metric doesn't. So this is an illustration of one of the corner cases. This happens to be not of interest to us for lingua franca because this is dealing with continuous time signals. But with lingua franca, it would be more relevant to Zeno signals, this generalization. See if there's anything about this. Yeah, so this same situation arises. Yeah, it turns out that there's a very interesting, somewhat counterintuitive result that strictly contracting is not the same as strictly causal. Eleftherios came up with a very nice counterexample of that, but I don't know if you want me to go through that. These are, again, there's a lot of work in dealing with corner cases to just sew up all of the different possibilities. Okay, and Eleftherios came up with a theorem that I've been calling the Matsikoudis strictly contracting theorem because it appears to be a new fixed point theorem, even though there's a whole family, there's a lot of fixed point theorems out there in the field of algebra. I've never, and to my knowledge, no one has found one that is exactly this one. But the statement of the theorem is that if you have a spherically complete generalized ultrametric semi-lattice, then a function f is strictly contracting if and only if for all causal f prime, when you compose f prime with f, there is a fixed point. Wild. But one way to interpret this, there's a very simple way to interpret this in the context of lingua franca. You can interpret this as saying that for any function f that is causal, not even strictly causal, not even delta causal, just causal, the outputs can be simultaneous with the inputs, that it will be, in fact, strictly contracting if you can find an f prime. Oh, it's the other way around. The f prime is causal. That the function f will be strictly contracting if you can find a causal function f such that f prime composed with f has a fixed point. And the practical interpretation of this from the perspective of lingua franca is you can draw the conclusion that every cycle has to have a delay that actually follows directly from this theorem. If you have cycles without delays, you have no assurance that of a unique fixed point, or even the existence of a fixed point. Okay. So the details of this get pretty gnarly, but they're well documented in Eleftherios' papers. There's also a constructive procedure, and this constructive procedure has some very nice properties. It again has the property that you can start with an arbitrary signal, but it has to, almost arbitrary signal. It has to have one fairly interesting property, which is that the signal you start with has to be a prefix of the result of applying your function to the signal once. Okay, so that turns out, if you go back to the case where I put the unit delay in the feedback loop, okay, this disallows starting with a signal with any events. In fact, the only possible signal you can start with is the empty signal. That's going to be the only possibility that will satisfy this property, because no signal is a prefix of itself delayed by some amount, except the empty signal. Oh, the way that this deals with Zeno signals is using a transfinite iteration. So so Eleftherios showed that you could construct a sequence of signals. It converges to a fixed point, but or rather, it converges to a least upper bound, But then you have to use that least upper bound and repeat the process in a transfinite iteration. So logically, you go through an infinite iteration to get to a point, then you repeat, and you repeat this, repeating an infinite number of times. So it's a transfinite constructive procedure. There was a bunch of follow-on work that I think Aaron Ames, who's a professor at Caltech now, did some work that used these results to talk about Zeno signals at some depth, and in fact ended up writing his thesis all about Zeno signals. So that's this Aaron Ames result. And these results about Zeno signals actually give very practical ways of building software that can actually construct Zeno behaviors in a practical way. Oh, I promised that I would relate to the little f. It turns out that this theory, that the constructive procedure can be used to define the notion of a firing function, which is the individual function that reacts to individual inputs and produces output events. Okay, you can give a formal construction for what that function needs to be. And this is what it looks like mathematically. It's a least upper bound between the function applied to the signal f and the function applied twice to this function to the signal s. Intuitively, you can think of this as a firing is the commonality between applying your function to the function that applies to the entire signal once versus applying it twice. That commonality between those two is a single firing. Okay, that's the intuition behind that. It's a way of finding an increment to the signal caused by one application of the function f. So this is actually an example. I think it goes through the iteration. Okay, so this is, you have a unit time delay in a feedback loop, and you're adding into that a signal that is got an event at every time unit with value 1, right? So the output is going to be, the first signal has value 1, so you get an output 1 at time 1. The 1 gets fed back with timestamp 2, gets added to the 1 that occurs here at timestamp 2, so the second value is going to be 2, then 3, then 4, then 5. You get a counting sequence out. Okay, so you can go through the constructive procedure. You start with the empty signal. When you apply the function f is this one, right? Given an input s, that's the function that's in the feedback loop. The green box is what's in the feedback loop. Okay, so if you apply this function to the empty signal once, you just get the clock signal. Right? The input is empty, so the output is the clock delayed by 1. Apply the function twice, okay? You apply, or rather you apply this same function to this signal, okay? And you're going to get the output 1 goes, why is this coming out at time 1? Oh, right, yeah. So this guy here is going to be delayed by 1 and added to the clock, which is going to result in this 2. But before that, the discrete clock produces an event at time 0 that comes out at time 1. Right, so you get this 1 and then 2s. The difference between these two signals is just this delayed by 1, 1. And you can think of that now as a single firing of this guy.
But don't they also differ in like their absolute value though for the future values? So like if after applying the function twice at t equals 2, starting from t equals 2, everything becomes 2 in magnitude.
Right.
Isn't that factor into the difference?
Yeah. Well, no, not exactly, because what this expression is actually the common prefix between these two signals. Okay, so it's the common prefix between these. So starting at time 2, these two signals differ. So this is a least upper bound in this generalized ultrametric space.
I see.
Okay, and the least upper bound translates into the common prefix. So the common prefix is this guy. Notice that if you keep applying this function f, right, you're gonna eventually get the counting sequence, right? You'll get 1, 2, 3 the next time you apply it, then 1, 2, 3, 4, then and so forth.
So is the intuition behind needing the second application to account for feedback, or?
This is kind of independent of feedback.
Well, I guess if you don't have feedback, it would suffice to execute just once, right?
Not really. Not really, because this discrete clock produces an infinite sequence.
Mm-hmm.
It produces an event at time 0, an event at time 1, an event at time 2, etc., forever.
I see.
So the output of this function is actually an infinite sequence.
Mm-hmm.
But the intuitive way to think about this is that you don't get that infinite sequence in one fell swoop. You get it by applying a firing function repeatedly. And this is a description of what that firing function does. Right? In a way, it's saying the firing function is going to give you one new output from the discrete clock added to whatever input got provided. Okay. The common prefix between the next two signals will be a value 2. No. It'll be the value 1 followed by the value 2. Okay, and the common prefix will keep growing, but the common prefix grows one event at a time. And that's why it's interpretable as a firing function. Okay. Yeah. So I think that's probably enough of an introduction to this, but hopefully that was useful. I mean, I think that basically these theorems would take very minor adapting to the lingua franca scenario. They're described in terms of firings when they talk about firings, but most of the theorems don't talk about firings at all. They talk about the entire behavior, right? And that'll apply directly to lingua franca without any modifications. In the case of, what they say about firings, well, we don't really have actor firings in lingua franca. We have reaction firings, so it's a little more fine grained.
Yeah, so it seems to me that we should probably look at figuring out the meaning of the composition operators in order to arrive at something that fits this description, right? Because we can order reactions within a reactor, for instance, that could then also be interpreted as something that probably, in principle, I guess we should be able to prove that we can describe an entire reaction program as an F, right?
Right.
But there are some steps in getting there.
Right. I mean, basically what you want is to be able to prove that that the capital F that you get from any lingua franca program will be strictly contracting in this sense. And then, you know, then the theorems give you your determinism result.
Well, thank you very much for the overview. This is very useful, and in fact, the slides themselves are very useful resources as well. So I'll go over those again.
Yeah, there's a lot of background in the earlier slides. So for example, if you're uncomfortable with the theory of partial orders and least upper bounds and stuff like that, there's a lot of tutorial material on that in the earlier slides in the series.
Yeah, thank you, Edward. I will also go over the slides again. I find examples like this one particularly helpful to me.
Yeah, me too. I mean, this whole theory is definitely one of those cases where, you know, I learned a lot from my students on this because they kept taking this in directions that kept surprising me.
So what is he doing right now? The student who come up with the theory, is he working on similar theoretical foundations stuff?
Eleftherios,
Yeah.
it's actually a rather sad story. He's unemployed.
Oh.
He's been suffering from some fairly severe health issues, and so he's living with his parents in Greece and is unemployed. I saw him just last October. I was in Greece, and you know, his health issues have stabilized, but he's basically not doing any work, and it's kind of unfortunate. There's also, you know, a fair amount of the work that he did as a postdoc, he's never published, and it's very beautiful stuff.
Wow.
But it's kind of esoteric. It's hard to get people to review it. I think, while he was going through these rather severe health issues, he had a rather nasty experience with a paper that he submitted to Theoretical Computer Science that, you know, they sat on it for a year and then summarily rejected it with a single review that was capricious. And, you know, everyone gets their papers rejected. And so, you know, what people normally do is pick themselves up, dust themselves off, rework the paper and submit it somewhere else. Mm-hmm. But in combination with his health problems, it just pushed him over the edge, and he ended up basically dropping out.
I see.
So, but that's, you know, I think that's really an individual situation. The other people who worked on this, Xiaojun Liu, is, last I checked, he was still working with a startup that he founded about 3 or 4 years ago that works on, it's called cloud physics. And it works on tools to help you evaluate which cloud infrastructures will work best for your application workload.
That's very cool.
Before that, he was working, when he first finished his PhD, he went to Sun Microsystems and was working on discrete event simulators for cloud infrastructure for Sun Microsystems, actually using the knowledge that he built up on this stuff to do that. And then Adam Cataldo went to the dark side and works in the finance industry. He's a quant.
Wealthfront, right?
wealth front. He's probably very rich and yeah, he's running his own hedge funds and stuff like that.
Yeah. So do you have any concrete suggestions for next steps to kind of marry this theory with what we're doing, just to kind of take this piecemeal and maybe, you know, get back and evaluate what we're doing next week or 2 weeks later?
Yeah, I think the simplest first step would be to determine under what conditions a lingua franca reactor can be asserted to be delta causal under the Cantor metric.
Mm-hmm.
Okay, and then that gives you a whole family of programs that will be proven deterministic using rather simple theorems.
Mm-hmm. I see.
And it'll also expose what the corner cases are. Under what circumstances do you get only strict causality and not delta causality?
Right.
Right.
Okay. Yeah, that sounds good. Yeah, maybe Shakai and I and Edward Wang also, if you're interested, we could start to work some things out.
It also requires, you know, very careful statement about how you're treating physical actions, for example. I think logical actions will be simple. Physical actions are going to be the harder one because it almost appears that there is no function f, right? And that would be one interpretation, actually, that there is no function f because it's not a function. There's many possible outputs. But there's a different interpretation, which is that for every possible instantiation of the physical world, there's a distinct function f. And for each function f, you get a deterministic behavior.
Well, it's not even the separate world, but also the origin, right? The time origin that you need, because you can execute the same program in the same world several times, but if the time origin is different, then you'll get different results.
Right.
So yeah.
Right. So there's kind of there's a very subtle argument about determinism there that needs to be thought through. Right. And the way that I've always thought about it in my head is to treat the timestamps assigned to the physical actions as part of the input to the program. And the way you handle inputs in this case, actually it's worth talking about that for a second, right? Because, you know, suppose you have a program where, you know, there's inputs that a user types at a keyboard, right? So how do those get into the program? Right. Well, one way to think about it is, you know, as a reactor with no input ports that produces on its output whatever the person types with the timestamps, you know, assigned to those. Okay, so that's the physical action scenario. And if you treat each such trace provided by the user as inputs to be a distinct f and a distinct program, that program ends up being deterministic. Okay. Another way to think about it is that these fixed point theorems are always about closed systems, right? Because I said everything is a function f in a feedback loop. There's no room for external inputs in that. So the way you have to represent external inputs is using a function f to represent the values of those inputs.
Yeah, it's not so different from kind of the assumed guarantee reasoning, right? Because there also you have to combine the system with its environment in order to say something about it, quite explicitly so.
Right.
So maybe we can also draw some analogies from that world in making our argument.
Yeah.
Mm-hmm. Okay, perfect. Yeah, let's figure out how we can kind of keep this ball rolling. I don't have a. I'm not really sure what we should do in terms of meetings and contact, but we can certainly start out with what you suggested, trying to characterize a subset of programs as contracting, and go from there.
Mm-hmm.
So I guess I feel like right now we have rather a set of theorems as a toolbox to tailor a more custom theorem for lingua franca and reactor systems in general.
Mm-hmm.
Right. So maybe we can maybe that's our future direction to create a more detailed and detailed proof suited for particularly for lingua franca, which is the platform we're working on right now.
Right. Yeah, I think that would be the goal. But my intuition tells me that it's not a long path to do this because there's a very strong theory that you can fall back on. You just have to show how lingua franca maps onto that theory.
Okay, I guess challenge accepted.
Okay.
And yeah, we'll work on it and circle back once we have more to discuss, I guess.
Yeah.
Okay.
Are we gonna chat offline about this more?
Yeah. Well, online, offline, or offline, online. I don't know.
Offline, online.
It's
Yes.
got to be online in some, in any case, right? Yeah, we'll do that. Well, thank you again, Edward. This was very, very helpful. So.
Thank you very much.
Okay. A pleasure. Oh, Xiaokai, I'm going to be going out this afternoon. Should I drop this picture by?
Oh, yeah, that would be amazing. Thank you so much.
Why don't you email me your address and
Okay,
I'll
that'd be great.
give you an ETA when I know better.
Wow, I'm so excited to see you in person finally.
That would be another good reason to do this.
Awesome. All right.
All right.
Let's do this afternoon.
All right. Good. All right. See you guys.
Bye-bye.
Bye.